So, in the last lecture we saw two major theorems. One was the monotone convergence theorem and the other one was Fatou's lemma. So, let us recall both of them. So, monotone convergence theorem. So, both these results help us in interchanging the integral and the limit. So, monotone convergence is always we will have a triple x f mu, x is a space, f is a sigma algebra and mu is a countably additive measure. We had fn's measurable non-negative functions and fn's increasing. Okay. In that case, of course, the limit will exist. So, limit fn x n going to infinity exists and we call that f of x. Okay. So, this is true for all x in x. Then f is measurable, that is easy because it is the limit of measurable functions, and this is the conclusion of the theorem. Limit n going to infinity integral over x fn d mu is integral over x f d mu. So, you can interchange limit and integration, right, fn d mu. So, this is what a monotone convergence theorem is, and we already saw an example of this when we studied measures. This was if we had sets a n increasing to a, so that would mean a and a equal to the union of all these a n's, then measure of a n increases to measure of a. That is precisely monotone convergence theorem applied to indicator function. So, you simply take fn to be equal to chi a n, but one can prove this simply by using the countable additivity of the measure mu. So, this was one of the theorems we saw. The second one was Fatou's lemma. In this case also fn's were measurable, non-negative. In this case we are not assuming fn's to be increasing, but we simply look at liminf of fn's. So, liminf of the functions fn. So, how is this defined? So, let us recall that this is simply liminf of fn x over n. Well, this is nothing but you take supremum of infimums of fk of x, k greater than or equal to n, and supremum over n, right. This is the definition of liminf. Liminf is also measurable. Fn's are measurable implies liminf is measurable, fn measurable, and Fatou's lemma tells me that integral of the liminfs is less than or equal to the liminf of integrals, liminf of the integrals, right. Integral fn d mu they are positive numbers and you take the liminf. So, this is what Fatou's lemma is. So, these two theorems allow us to interchange the limits and integrals in many cases, but both of them deal with positive functions. Well, sometimes the positivity is not necessary, but this depends on the context, depending on what kind of functions you have. For example, you may be able to subtract some things or add some things and make functions positive, and then apply Fatou's lemma. We will see instances of such things when we go ahead. Okay, so we have one more theorem of this kind which will allow us to interchange the limits and integrals. But before we state that, let's prove simple result which we already know in the case of summation, but we will prove this in the general context of integration. So, let me write it as a proposition. So, as usual we have the triple x f mu, and let us take f in L1 mu. So, recall that this is same as x f mu. So, whenever we write a measure, the space and the sigma algebra is understood, it exists. So, x and f will exist. So, recall that this is simply all complex valued measurable functions such that integral over x mod f d mu is finite. So, class of integrable function. So, we call this class of integrable functions. Now, so if I take an f in L1 mu, then the conclusion is modulus of integral of x f d mu is less than or equal to integral of over x mod f d mu. So, everything makes sense here. So, first of all let's make sure that we understand this. So, I am taking a, so call this as remarks if you like. We are starting with a function in L1 of mu. What does that mean? That means integral over x mod f d mu is finite. Okay. Recall that f is a complex valued function. So, this is a complex valued measurable function. Okay. And so, I can write f as u plus I times v, where u and v are both the functions u and v are real valued measurable functions. Real valued measurable functions. So, we are writing f equal to, so let's recall that. So, we are writing f equal to u plus I v, and if I look at mod f is of course bigger than mod u and mod v. So, we have mod u less than or equal to mod f, mod v less than or equal to mod f. Now, u and v are measurable. So, mod u and mod v are also measurable. So, both of this gives us, by monotonicity of the integral, we have integral over x mod u d mu is less than or equal to integral over x mod f d mu, which is finite. Similarly, integral over x mod v d mu is less than or equal to integral over x mod f d mu. Both are finite. So, both these functions are, so both u and v are actually in L1 of mu. As a result, if I look at integral over x f d mu, so whatever discussion we just had implies that integral over x f d mu is nothing but, well, I know that this is by definition because of the linearity of the integral, I have this quantity and each of them is finite, right, because of these two properties. So, let's elaborate on that. So, u, I know that mod u d mu is finite. This implies, so we write u as the positive and the negative part, u plus minus u minus, and mod u is nothing but u plus u minus, right, because u is real valued, right, u is real valued. And integral over x mod u d mu is simply integral over x the positive part plus integral over x the negative part. Negative part is a positive function, by the way. u is u plus minus u minus, right. So both of these are finite because this is finite. So this is a finite quantity, this is a finite quantity. This will imply that integral over x u d mu, which is the difference of two finite positive numbers. So that's also a finite number. So this is an element in R, it's a finite quantity. Okay. So going back, so similarly for V, right, because V is in L1, mu implies both V plus and V minus will be in L1 of mu, and so integral over x V d mu is equal to integral over x V plus d mu minus integral over x V minus d mu. Both are finite. So this is a real number. So all this would imply that if I look at f d mu, this is of course integral over x u d mu plus I times integral over x v d mu, and this is finite, this is a finite quantity, this is another finite quantity. So this is like alpha plus I beta, so it's a complex number. Okay, it makes sense. So this is a fixed complex number and we are trying to prove that. So let us go back to the statement of the result. So we are trying to prove this inequality. Okay. So the left hand side makes sense. First of all, it is an integral over x f d mu, it's a complex number and I am taking the modulus of that. So I will get a positive number. I want to say that is less than or equal to integral over x mod f d mu. Mod f is a positive measurable function. So its integral makes sense. It may be infinity or finite, but we are assuming f to be in L1, because if it is already infinity there is nothing to prove, but we are assuming f is in L1. So this is a RHS is a finite quantity. Okay. Alright, so let us try to prove this. So proof is sort of one line, but it's something which we use every now and then. So take alpha in the complex plane, mod alpha equal to 1 such that alpha times integral over x f d mu. So remember, integral over x f d mu is a complex number. I am taking another complex number alpha such that mod alpha equal to 1, so that this is actually equal to the modulus of the complex number we started with, right. So this we can do. So what we are doing is, if I take a z in the complex number, there exists alpha such that mod alpha equal to 1 and alpha times z is equal to mod z, right, because if, for example, if z is 0, any alpha will do, right, any alpha such that mod alpha equal to 1 will do. If z is not 0, then what is alpha? Alpha is mod z by z, right, because of this mod alpha is 1. Okay, so that is the alpha I am taking. I know what is integral over x f d mu is, it's a complex number, so there is an alpha like this. Okay, so let us continue with the proof. So let's start with the right hand side. In x f d mu, this is equal to alpha integral over x f d mu, which by linearity, now alpha is a complex number, right. So when I integrate, it will go inside the integral due to linearity, which is integral over x alpha times f, that is my function d mu. This is by linearity of the integral, the alpha goes inside, which is equal to, so let us look at this again, the right hand side. So this is a complex function, complex valued function, but the left hand side, this is a positive function, this is a positive number. Which means the imaginary part of this would be 0, right. So this I can write as, so let me write one more step so that this is clear. This is real part of alpha times f d mu plus I times integral over x imaginary part of alpha times f d mu. That is how you write it because of linearity, but this will have to be equal to 0 because the left hand side is a positive number. So, because of that the imaginary part will have to be 0, which means I can erase this part, right. They will be equal to the integral of the real part, but it is positive, right. Well, so I can write this to be less than or equal to integral over x modulus of alpha f d mu. Why is that? Because if I look at real part of f, I know that this is less than or equal to, well, real part of any function g, real part of any function g is less than or equal to mod g. So, integral over x real part of g d mu will have to be less than or equal to integral of mod g d mu, right. So, that is all I am using here, right. This is from this inequality, but alpha has modulus 1. So, this is simply x mod f d mu. So, that is the proof, that is one line proof. So, integral, the modulus of the integral is less than or equal to the integral of the modulus. So, let me tell you that we have seen a case of this. So, let's recall that. If I take, suppose ANs are complex numbers, okay, then we know that if I take summation AN n equal to 1 to infinity, modulus of this is less than or equal to summation n equal to 1 to infinity modulus of AN. This is something which we know, and this is precisely this inequality, right, because the summation is an integral. Summation is an integral. So, I can write summation n equal to 1 to infinity AN as integral over x f d mu for some suitable x and mu and f, and this tells me that the summation modulus of the summation is less than or equal to sum of the modulus. That is precisely this inequality. Okay, let us continue. Now, we come to one of the most important theorems. So, this is called the dominated convergence theorem. So, Lebesgue's dominated convergence theorem. Dominated convergence theorem. Again, this is one of those results which allows, one of the most useful results in measure theory, which allow us to interchange limit and integrals. So, we will call this DCT, dominated convergence theorem. So, let me state it. So, I have x f mu as usual, and I have a sequence of measurable functions. So, let fn be complex valued. So, now you see it is complex valued. The earlier two theorems, the monotone convergence theorem and Faddu's lemma, required that the measurable functions be non-negative. Here we are looking at much more general class of complex valued measurable functions. For n equal to 1, 2, 3, etc., we have a sequence of measurable functions such that the limit exists. So, limit n going to infinity f n x equal to f of x. Okay. So, f of x then will be automatically measurable, right. So, then as a conclusion we know that f is measurable. Okay. Suppose there exists a function g in L1 of mu. So, an integrable function such that mod fn is, so mod fn at x is less than or equal to g of x for every x in x. Okay. So, and for every n, right. So, g is called the dominating function. So, g dominates all the fn's. In that case, so here is the strong part of the conclusion. In then f is in L1 and integral over x mod fn minus f d mu goes to 0 as n goes to infinity. Okay. In particular, we also have limit n going to infinity integral over x fn d mu equal to integral over x f d mu. So, again here you are interchanging. So, this is interchanging limits and integration. Okay. So, there are conditions. One is fn's, we have measurable functions, limit exists, and more importantly there is a g which dominates. So, this is the dominating function, right. The dominating function g has to be integrable. Okay. So, there is a control on the way fn's grow in some sense. In that case we have this convergence. This is a rather strong convergence, we will see it later. In particular, we can interchange integrals and limits. So, proof of this, well, proof is not all that difficult once we have Fatou's lemma, but it is an extremely useful result. We will see some examples soon. So, let us prove the stronger statement that fn's are that fn's converge to f in some sense. Okay. So, first of all f is measurable, that is trivial. Okay. Then all fn's are dominated by g for every x and for every n, but f is the limit of, since f of x is given by the limit of fn's, we immediately get that mod f of x is less than or equal to g of x for every x. Okay. Well, which also implies by monotonicity of the integral mod f d mu, if I integrate, I am going to get something less than or equal to g d mu, which is finite because I know that g is in L1. So, this implies that f is in L1. So, this much is sort of straightforward from the monotonicity of the integral. So, now what we do is we look at, so consider these functions. So, look at 2g. So, remember g is my dominating function minus modulus of fn minus f. So, for each n, so this is a sequence of measurable functions, right, sequence of measurable functions. So, what does it mean? So, for each x we are looking at 2 times g of x minus mod fn x minus f of x, right. But recall that fn's are bounded by, recall that fn's and f are bounded by g. Mod f of x is also less than or equal to g of x, right. This is true for every x. So, this gives me that these are positive functions. So, I have a sequence of positive measurable functions. I can apply Fatou's lemma. So, apply Fatou's lemma to the sequence of functions 2g minus mod fn minus f. Remember, these are positive measurable functions. So, I can apply Fatou's lemma. So, what does Fatou's lemma say? integral lim inf is less than or equal to lim inf of integrals of these functions. So, we get integral lim inf of the functions we are looking at, that is 2g minus mod fn minus f d mu is less than or equal to lim inf of the integrals. So, lim inf of the integrals of the functions we are looking at, mod fn minus f d mu. Well, so let us try to compute this. What is the left hand side? Since fn's are converging to f, since fnx converges to f of x for every x, lim inf of 2g minus mod fn minus f will be equal to 2g because of this part going to 0. Similarly, on the right hand side, this is 2 elements. So, I have two pieces. So, I can look at 2g d mu as a separate thing, and I have plus lim inf of integral over x minus mod fn minus f d mu. So, remember the minus is put inside the, because I will be taking the lim inf, right. So, this is, so let me write it again, integral over x 2g d mu plus the minus will come out of the integral, but not out of the lim inf. So, let's write one more step, lim inf of minus integral over x mod fn minus f d mu. So, I am taking some positive numbers, looking at its negative and taking the limit. Okay. So, let us compute this again. So, on the left hand side we have LHS is simply integral. So, I know that this goes to 0, what remains is simply 2g. So, it is integral over x 2g d mu, I know, and this is less than or equal to integral over x 2g d mu. Now, what I have is lim inf of negative thing. So, here is a simple exercise, lim inf of, so I take sequence an positive and I take lim inf of minus ans. Okay. This is minus of lim sup of ans. So, apply that, we will get minus lim sup of integral over x mod fn minus f d mu. So, this is the inequality we have. Now, recall that G is in L1, G was in L1. So, these are finite quantities, right, these are positive numbers, G is a positive function. So, I can cancel this. So, I can cancel this. So, what do I get? I get, here I have a positive number, then I have a negative sign, and here I have cancelled, I will get 0. So, I am getting 0 less than or equal to minus lim sup integral over x mod fn minus f d mu. But this is a positive quantity and minus of that will be a negative quantity, and that is positive. This implies that lim sup of integral over x mod fn minus f d mu is actually equal to 0, right. But lim sup of positive things are 0, meaning the limit itself is 0. So, limit of integral x mod fn minus f d mu is 0. So, that was one part of the theorem. So, let us go back to the statement of the theorem. So, what we have proved is this part. Okay. This is an easy corollary or easy consequence of what we have just proved. So, let me write that as well. So, from this conclusion, so that is a stronger conclusion. So, integral, so we already have integral over x mod fn minus f d mu goes to 0 as n goes to infinity, that is what we just proved. Okay. Now, if I look at integral over x fn d mu, I know this is a complex number minus integral over x f d mu. I want to say that the left hand side sequence goes to the right hand side number, right. This is what we want to prove. So, to prove that, I look at the modulus of the difference of these two numbers. Well, integral is linear, so you know that this is fn minus f d mu and then modulus. Okay. Then we use the inequality we proved. So, what is the inequality we proved at the beginning? If I take a complex valued function g and I integrate and take the modulus, I know this is less than or equal to modulus of the integral. So, this is less than or equal to integral over x mod fn minus f d mu. I know this goes to 0. Okay. So, this sequence converges to this sequence, this number, that is the. So, integrals converge and you can interchange limits and integration. So, let's see how this is used. Okay. So, let's put this as a remark. How does this get used in various places? So, let us take a special case, okay, where mu of x is finite. Okay. Well, what is the big deal? If the measure of the whole space is finite, if the measure of the space x is finite, then constant functions are integrable. Constant functions are integrable. Okay, what does that mean? So, if I take f from x to c, f of x equal to k for every x, k is some fixed complex number, fixed complex number. It could be 1, 2, I or any such fixed complex number. Then of course, f is measurable, that is trivial because it is a constant function. And if I look at integral over x mod f d mu, well, this is equal to integral over x, mod f will be mod k, which is a constant, and that comes out. So, mod k comes out, and what remains is the total measure of the set, that is x, and this is finite. So, such functions are in L1 of mu. So, in such a case, suppose we have measurable functions fn, complex valued measurable functions, and I know that mod fn's are less than or equal to, let us say, some fixed constant k, okay, k a positive constant. Suppose limit n going to infinity fn x exists, and let us say it is equal to f of x for every x, okay, then I can conclude that integral over x fn minus f d mu goes to 0. Well, why is that? Apply dct. Apply dct. What is the dominating function? The constant function. The constant function is the dominating function. Is the dominating function, right? Because it is in L1, and you know that if I have sequence of measurable functions bounded by a dominating function and you have convergence, then this happens. Now, you see, this is much more powerful than the Riemann integration. In Riemann integration we needed uniform convergence for changing the limit and the integration. Here we have only pointwise convergence for every x, but bounded by a dominating function, and if you have that you can interchange limits and integration. Okay, so we will stop this session with just recalling what we did. The main theorem we proved today was the dominated convergence theorem, which is extremely powerful. Comparing it with Riemann integration, where you require uniform convergence to interchange limits and integrals, here we just need pointwise convergence, but with a dominating function. The dominating function should be in L1. If the space has finite measure, then it is enough to look at a dominating function to be a constant. Of course, all the time the constants may not work, but most of the time that is what works. You will see examples as we go along.